All right. Back to we're done with the potential energy. Sorry, we're done with potential energy and the change in the potential energy and the relation between the work done on the object and the change in the potential energy of that object. All right. Now we will come to the kinetic energy. Kinetic energy, as we all know, it's half mv squared. And if you say there is also something called change in the kinetic energy, which would be half m v final square minus v initial square. So if I just say here, let me just see the comment. All right. And then here I can proceed. Okay. So here, if I will say just that there is something called kinetic energy half mv square, and there is something called the change in the kinetic energy. Okay, the change in the kinetic energy. All right. Okay, which is equal to half m v final square minus v initial square. Or of course you can say half m v final square minus half m v initial square, but of course this is the easier one to deal with, okay, since we are dealing with the same object. So this is the change in the kinetic energy. Okay, let's come to some examples here. It says a 2.5 vehicle, it travels down the highway with a change in velocity. See, it's the change in velocity between or of 80 km per hour to 110 km per hour. Calculate the change in the kinetic energy, all right, which we just mentioned here. Since it's the same object, so it's half m, all right, v final square minus v initial square. Where is v final? It's the 110 and the v initial is the 80, but we have to pay attention to the units here. The units here, the mass is in ton. Ton is 1,000 kilogram, all right? The ton, 2.5 ton vehicle. Okay, this is the ton is the 1,000 kilogram. So we convert the mass into kilogram by multiplying it by 1,000. Now here, we've been through that again earlier, and we mentioned that how to convert kilometer per hour. For example, I will do it my way and the book way also. Kilometer per hour, and you can do it like that. This is 1 hour and it has 60 times 60 seconds, and then also the kilometer will be down and it has 1,000 meter, because kilometer will go with kilometer, hour will be with hour, and we end up 80 times 1,000 divided by 3,600. I would go with this way. It is safe. You will never make a mistake here. I would advise you to do that. So we convert the velocities, we convert the mass, and now immediately we say delta Ke, which he's asking the change in the kinetic energy, half mv final square minus v initial square, which is equal to this number in joules. All right. So what we have in this problem? We have a vehicle and it changes the velocity from 80 to 110. And that basically lead to, of course, changing of the kinetic energy in that object. All right, let's see the second problem, or the second concept. It is the relationship between the kinetic energy and work. And I would say it is not literally the relation between kinetic energy and the work. It's between the work and the change in the kinetic energy. Okay, keep this in mind. It's like the above, it was the work and the change in the potential energy. So here we have the relation between the work and the change in the kinetic energy. So here we have, when a body of mass m has its speed increases or increased from V initial to V final at a distance x by a constant force F, okay, which produce an acceleration A, right? So if an object is basically changing its velocity, that will during a certain distance, this what happened in this problem, that he changes the velocity, all right? Of course, you will change the velocity along a distance, a certain distance. So that reminds us with Newton or with equations of motion, V final square is equal V initial square plus 2ax. So the change in the velocity will cause basically an acceleration. So the change in velocity will cause acceleration. All right. If we multiply everything by half m, this is just as a derivation, you will see that half mv square is equal to half mv initial square plus half m times ax, which will be max. If you see here something, this is ma, which is the force, times the distance. So this is F times X. What is this relation? F times X, it's the work. It's the work. And this is the change in the kinetic energy. So the change in the kinetic energy is equal to the work done on this object. All right? I will add something here, okay? I will add, this is called the network, which is of course F times D, or X, whatever the distance, okay? F times D or X, okay? So this is the network. We will come to explain why it is the network, while in the potential energy it's only the work. But we will come to that. But for now, you should understand the work net is equal to the change in the kinetic energy. Okay. Let's come to an example. A car of mass 1,000 kilogram traveling at 30 meters per second has its speed reduced to 10 meters per second. So we have mass, we have V initial is equal 30 meters per second, and we have V final, it is 10 meters per second, okay? All right. By a constant braking force over a distance of, so X is given 75 meters, find the change in the kinetic energy. All right, find the change in the kinetic energy. This could be a very simple example, half mv final square minus half mv initial square, and that will be the change in the kinetic energy, right? And number two, the braking force. Okay. What is the force? It's m times a. M times a. Do we have the mass? Yes. Do we have the acceleration? No. Can we calculate the acceleration? Yes, we could. From this equation, V final is x squared is equal to V initial squared plus 2ax. Do we have x? Yes, we do have x. So what we did is we calculate the a, okay, and m times a will be the braking force, right? So this was the change in the kinetic energy. It was negative because he was slowing down. And okay, here the solution is different. Here the solution is different. It says we know that the work is equal to the change in the kinetic energy. The change in kinetic energy is minus 400K. All right, 400 kilojoule. Here we should have said kilojoule. 1 minute. Okay. Now the distance is known. The work itself is F times D. So we just simply divided this by 75, and the force will be this number. Now the one I approach was longer. it was through V final square is equal V initial square plus 2A delta X. So from here, you will find the A, and F is equal M times A, all right? And okay, but since we already, and that's absolutely correct, you can try and find it out. It's absolutely correct. But here, basically, you are having already the change in the kinetic energy, which is equal to the work. And the work itself is F times the distance. So you don't need even to go through calculating the acceleration and then the force. You immediately say force times distance is equal to the change in kinetic energy, which already you calculate in part A, and simply you say the force is equal that change divided by the distance, and this will give us the force in Newton. This is one of the very important problems because it basically it connects between the change in the kinetic energy and the work done on the object. All right, guys? Okay. Now we will talk about conservation of energy. If I would be in the class today and I will be asking you, what is the conservation of energy? I know that many of you will say the principle of conservation of energy is that the energy of the system remains constant. Energy cannot be created or destroyed, but may be converted from one form to another. I know that most of you, they know, and I used to enjoy to hear it from the students, that how they really know it in very nice rhythmic way. Energy cannot be restored or created or destroyed, but it might be converted from one form to another. Okay. Now, the total energy that the object can have, and we write it down maybe in the beginning of this chapter, it was the mechanical energy, we wrote it. Initial is equal to mechanical energy final. And if you remember, guys, when we discussed at the beginning of the chapter, only when I was going through the concepts and the sections that we will cover in the chapter, we say, what is the mechanical energy? It's the total potential energy of the object plus the kinetic energy of that object. Okay, so if we say initial is equal to final, because the energy cannot be created or destroyed, so the mechanical energy at the beginning, it's equal to the mechanical energy at the final stage. So each mechanical energy is anyway potential energy plus kinetic energy. And here, this is the meaning of conservation of energy, that basically you can write it the summation of energy, or you can set the mechanical energy initial and final. All right, so now here, if you see, if we call this as our reference level, all right, and we say that the object has gone through a free fall. Free fall means that velocity was zero initially, all right? What is the potential energy at this point? It is mg times h. What is the kinetic energy at this point? It's zero, all right? So at this point, let me write here, at this point, the potential energy is equal mg times h. The kinetic energy is equal to zero, because V initial is equal to zero. Now, the object dropped and it reached now to the reference level, which is zero. So at this point, what is the potential energy of the object? It's zero. What is the kinetic energy of this object? It's half mv final square. So in this situation, the kinetic energy is the maximum and the potential is minimum. While in this situation, the potential energy is maximum because the kinetic energy is zero. I will see you in the next YouTube.